looking at many of these quadrature or QAM-modulated RF signals. And so I put together this little bit of an assembly here to kind of show the Qpsk modulation. I have a pair of mixers. Each of them is doing essentially that BPSK modulation. They're being fed with carriers that are in quadrature, and I've got them fed with digital signals to create the modulation. So let's zoom in on the scope screen and see what we've got. We zoom in here. We can see that here's my digital signals here, and they're varying. Both of them are varying between, essentially a negative and positive value. So they're both negative, and that one's negative. This one's positive. This one's positive. That's positive. And this one is positive, and that's negative. So those are the four states that we talked about. And you can actually see how that's now affecting the carrier. So we're jumping a quarter cycle from here to here at that transition. We're maintained in that phase, and this transition is jumping us another quarter cycle, and so on. This transition is causing another quarter cycle jump. So this is what the carrier looks like and how the phase changes for a Qpsk signal. So of course, that would be represented by those four constellation points, equal amplitude, okay, in all four states, but a different phase in all four states. Which is really just two more aspects of this. The I and Q signals.
Lost the buffer.
Don't necessarily have to just be ones and zeros or plus ones and minus ones. They can be essentially any analog value. As we discussed earlier, we can essentially create amplitude, frequency, or phase modulation by simply amplitude modulating these quadrature carriers. So really any modulation type, AM, FM, PM, single sideband, double sideband, BPSK, QPSK, whatever it might be, any modulation type can be represented by the appropriate generation of I and Q waveforms. And this is a very common thing in software-defined transmitters because these baseband signals are relatively low frequency and they can be synthesized very easily in hardware. And then, or even in software, and then fed to a D to A converter, for example. Even all of this processing many times will happen digitally. So we can create any RF signal with just simply quadrature carriers and the appropriate I and Q. Of course, all this works in the opposite direction just as well for demodulating signals. Essentially, if you take any RF signal and then demodulate it with quadrature local oscillators to create the I and Q data streams, there is enough information in the I and Q to fully demodulate that signal, whether you're doing it for receiving the signal.
Kevin, ist das schon der Compiler das Ding?
So I think it's not a bad point to stop here.
What's buffering now?
I think just to recap what
To listen to it, or to grab data out of it, or to analyze the signal. Once you've got this.
So let's just recap what he's saying. So he's saying you can have an oscillator, and if we apply I and Q signals 90 degrees out of phase to this, we can generate any modulation and any combination of amplitude and phase. And that's for demodulation as well as modulation. We just turn the concept around. So that's in essence what he's saying. So if you look at SDR, there's USB dongles. All I'm sending is 2 bytes, which is the I and the Q, and a continuous stream. The rest is all done with mathematics. So if you think what is happening there, this is a little, no. This is the oscillator, and there's the RF signal coming in, and there's your I and your Q coming out. That's what it's at. The only difference is this one is 90 degrees fed compared to the bottom one. So as simple as that. It's a concept we've never actually looked at, and if you look at quadrature itself, that's it. And so the question is, the next step then, once you've done this, is how quickly can you sample these two analog signals that's coming out here, with the analog to digital converter. And that gives you the spectrum, and the bytes gives you your definition in dynamic range. So you can have maybe a 60 dB or 80 or 120 dB range. So the bigger the dB range is, the less is the capability of adjacent channel disturbance. The less the dB range, the more the chance of adjacent channel disturbance. So that's really what you do. And with some of the mathematics, you can now interpolate. I always struggle with that word. Mathematically create those little dots in between. So you can sort of simulate signals. So you can even take it the next step where you can actually now do filtering of signal which doesn't even exist in the incoming A2D, but you're simulating it because there's a very good chance that you will be quite accurate at it. Yes?
That quadrant, or whatever you call it?
Yes. Quadrature circle, yeah.
It's on even on the SDR, I see on your SDR and on the PSK program, you can actually see the signal going left and right.
Correct. Some of this
graph in the software.
SDRs has got that little window. You see the actual dots appearing all over the place. So yeah, they've got in the SDR, most of the SDR software.
I thought that was for the antenna rotator. I thought that I was antenna was finished.
The sun is coming.
So you live differently.
I was wondering why it was going so berserk last time I looked at that thing. But I didn't even have an antenna rotator and that thing was spinning.
So this one is taking it further, and how to build some of the modulators and demodulators.
Right, a test after this.
Yes.
80% pass mark.
So I mean, we don't have to go through the whole thing, but if you guys are interested in the FM, AM, we can watch. Do you want to watch a movie?
Yeah.
Okay.
Anton, I don't know what use my connection. I've got LTE, so it should button quickly.
I can maybe connect to you if you think it might help. I don't know. I've got LTE as well. I don't know why it's just.
The MTN or Verticon?
We just put in.
Telcom.
Oh, that's
A lot of these stuff in a simple diagram. I understand what they're talking about. Because they're using those now all of a sudden he's talking.
It's just the 524. How much data do you have, Justin?
Maybe September, October, November, December, I'm going to have nothing. Coming out, you just have to select the right one. There's really all that. That's what I said, there's all of a sudden, this is, now you see why was on those diagrams?
It works all five
Justin, did you say you can slow loading? What speed you got?
In our previous video, which I'll link below if you haven't seen it, we discussed IQ signals and how they can be used to represent basically any type of modulation or variation in an RF signal. Not only they can be used to generate any type of modulation, but they can also be used to analyze any type of modulation. So in this video, we're going to explore that just a little bit further with a couple basic modulation types. So we'll take a look at AM, amplitude modulation, FM or frequency modulation, and also talk about how these techniques can be used for single sideband signal generation. Now to illustrate this, what I'm going to do is use one signal generator to generate some of these signals. And then on the bench here, I've put together that same set of mixers that we're using essentially in this configuration here, where we're going to essentially demodulate down to the baseband quadrature components. This signal generator back here is going to be used to generate the modulated RF signals. This signal generator here is being used to generate my quadrature clock, or my quadrature LO, And we're doing a direct conversion through these two mixers. So the output that we're going to be looking at on the scope is going to be just the baseband I and Q signals. These two signal generators have their references locked together so that way when I set up a carrier frequency for the modulated signal and the direct conversion quadrature oscillators for the mixers, they're going to be phase locked together so everything will be perfectly stable. That will make it very easy for us to go examine the IQ signals in a nice stable way. So let's look at amplitude modulation first. So, quite simply again, the amplitude modulation is where the amplitude of the RF signal is modulated by a low frequency signal, typically a baseband signal. And when we talked about the phasor diagram for the quadrature signals, we basically said that amplitude modulation is simply when the I and Q components vary by the same amount. So essentially in the phasor diagram, the length of that vector simply grows and shrinks. Okay, so we basically don't change phase, we're only changing amplitude and moving that up or down because the I and Q signals are moving up and down. So I've got the signal generator set up to generate an amplitude modulated signal that essentially is in phase with the Q component. All right, and it's amplitude modulated with a 2 kilohertz baseband frequency. Well, let's take a look at what that looks like on the scope. Spin around to the oscilloscope. And the scope is displaying both the I and the Q components. And as I mentioned, I've got the phase aligned so that there is no I component at all. So we see the DC on that. And I can see the Q component varying sinusoidally. And if we put a set of cursors up here, we can go measure that baseband frequency right around 2 kilohertz, just as we expected. So that's what it looks like in the time domain. Let's look at the phasor diagram. So we just turn the scope down into XY mode, turn these cursors off, and we can actually see just the vertical bar because we're varying that amplitude up or down. Now it's not real clear that that's really what's going on there, but this does give us a nice way of essentially viewing that vector that we would normally see here. And that vector in this case is just kind of going vertically up or down. If I slow the amplitude modulation baseband frequency down, let's bring it down to say 1 hertz, now you can actually see the amplitude varying of just that Q component with the I component being 0. Now for the purposes of visualizing that vector, that phasor, let's keep the baseband frequency up high enough so that it looks like a nice solid line. Now I can actually see what's going on. If I vary the phase of this signal, I can actually change where that vector is, and I'm just changing the phase and then stopping it. And all we're doing now is creating essentially a new vector, with establishing a different phase between the baseband or the RF signal and the IQ signals that we're using to demodulate it. So again, from essentially a phasor diagram standpoint, an AM signal basically is one that we are represented by a vector length that is changing, but not necessarily where the phase is changing. So let's take a look at FM. So before looking at frequency modulation, let's first take a look at what happens when you just have a frequency offset between the carrier signal and the local oscillator. And here's one way to look at it. Let's say this is our local oscillator and this is our incoming frequency. What we can see is that after the first half cycle, there's a little bit of a phase slip. After the next half cycle, that phase slip or phase delta is a little bit larger. Next half cycle, it's larger again, and so on. So phase difference looks like a continuous change in phase over time between the two signals. So let's look at what that means in terms of our IQ signal components. So if we look at our phasor diagram, remember that the length of that vector essentially is equal to amplitude. But for frequency modulation, we're not going to change the amplitude. But what we said was that the phase is going to vary continually over time. Remember, the phase is represented by this angle here. So what that means is that if you have a frequency offset, this vector is in effect spinning in one direction or the other around this circle. basically describing out a circle because the amplitude is not changing, so it'll be a constant amplitude circle where the phase is varying continually over time. Now, how fast that's spinning around is equal to the phase difference between the two signals. Right? If we go around 360 degrees in 1 second, then that's a 1 hertz frequency difference. If we go around 1,000 times a second, that's a 1 kilohertz frequency difference. Now, the direction that we're going around is basically dictated by which signal is leading, or which one is faster. If the I and Q signals are faster than the incoming RF signal, the vector will spin in one direction, and if the opposite is true, the vector will spin in the other direction. So what does that do to our IQ signal components? Remember, the I and Q components are really the coordinates, if you will, of the in-phase and quadrature components of that vector. So if we picture this thing spinning around here, we can kind of pick some points off and say, well, if the vector was sitting right here, right, the I component will be out here, but the Q component will be right there. As this vector rotates up to here, the Q component advances up to that point, the I component comes down here. And we can continue going around here and actually see that we're tracing out two sinusoids for the I and the Q as this vector rotates around. The other thing that you'll notice is that these two sinusoids are also in quadrature. Where we started off, this is essentially a cosine wave starting at the peak, coming down and going around, where the Q is more of a sine wave starting at 0 and going around. So really a frequency offset is represented in the Phasor diagram or by the IQ components as a pair of quadrature sine waves whose frequency is equal to the frequency offset. And depending on which one of these guys is leading, okay, which one is essentially occurring first, dictates the direction or the frequency offset. So let's take a look at those signals. Again, here's our amplitude modulated signal at a basically phase locked to the LOs. What I'm going to do is now introduce a 1 hertz frequency difference between my modulated RF signal and the IQ signals, the LO signals. Okay, and you can see what I'm doing is now is causing that phasor to rotate at a once per second rate. That's because we have a 1 hertz frequency difference between my quadrature local oscillators and the RF signal. If I make that 2 hertz difference, we'll rotate twice a second, 3 times a second, 4 times a second, and so on. Okay? So that's essentially a frequency offset is represented by essentially spinning that vector around, or essentially a IQ sinusoid, quadrature sinusoid for the I and Q components. So this spinning vector is representing just a constant frequency offset from the LOs. Now, of course, FM means that we're varying the frequency as a function of our baseband signal. So if I take and bring that frequency offset back to 0, and I change my modulation type from, let's change it from AM to FM, okay? Now what we're seeing, I'm generating an FM signal here that has got a 1 hertz baseband frequency, so I'm spending essentially a half a second spinning in one direction where the carrier frequency is higher than the local oscillators, then the other half a second spinning in the opposite direction when the carrier frequency is below the local oscillators. So obviously if I speed up the baseband signal, this would spin so fast that you wouldn't really be able to see it. So I purposely kept the baseband frequency very low so you can see the effect of that vector spinning in either direction for an FM signal. Now, of course, what's happening is when we're getting that reversal in the spinning of the vector, what it really would represent, if you looked at it in the time domain, is that in one case the Q signal is going to be leading the I, and in the other case the I signal is going to be leading the Q. So by essentially reversing that situation, we can basically, when we modulate a signal, create a positive or negative frequency offset. So So one way to think about that is if I have a pair of sinusoids in quadrature, if I take one of them and I invert it, it essentially makes it, it look like the other one is leading. So if this guy was leading and this one, but then I inverted this signal, it would look like this signal is leading. So inverting a sinusoid is just like adding a 180-degree phase shift.